Stangibelisco here with one more little video having to do with quarter wavelength sections of transmission line. What you're looking at here is an antenna design that has been used in practice. It's a variation on the well-known J-pole antenna design, but instead it's something that I've always wanted to try for 160 meters or 80 meters. I would connect a half wavelength antenna to one side of a quarter wavelength section of ladder line. Now this ladder line has bare conductors with plastic spacers at intervals of about 6 inches, and I believe that it comes in two varieties, the so-called 300 ohm and the so-called 450 ohm varieties. The 300 ohm variety is spaced at a couple of, about 1.5 centimeters apart, and the 450 ohm variety about 2.5 centimeters apart. So maybe a ½ inch for this stuff here, 300 ohm and 450. Now it doesn't really matter which impedance you use for this ladder line in this antenna design. It is very important that the antenna be a half wavelength according to the formula 467 divided by f in megahertz. So for example, if I were to go with a 160 meter design, 467 divided by, let's just say, 1.810 megahertz, 258 feet. So you'd want to fly a kite or balloon to support that antenna, or else get it as high as you possibly can. What you do then to the far end of this transmission line, that is the non-antenna end, is you short it out. You have to make sure that this line is very close to a quarter of a wavelength. Now if you have, say, a transmission line with a velocity factor of 90%, then the formula is 492 times the velocity factor, so 492 times 0.9 divided by, pardon me, yes, no, for a quarter wavelength section it's 246, half of 492 times the velocity factor 0.9 divided by the frequency in megahertz. 122.32 feet, or about 122 1/3 feet, or 122 feet 4 inches. Now you'd have to tailor that by experiment, and there are test instruments that can help you to do that, and you can also get the exact velocity factor of a line like this from the manufacturer, and then you calculate the length of that line according to the formula 246 V divided by the frequency in megahertz, where V is expressed as a ratio. Okay, so there's the design, and you short circuit this. Now when you do that, you get in effect a continuous impedance transformer where you're going to have pure resistances all the way along this line. At the left-hand end over here, you will have a short circuit or a purely resistive impedance of 0 ohms. At this point right here, you will have a purely resistive impedance of whatever the radiation resistance of this antenna turns out to be. It'll probably be somewhere on the order of 2,000 ohms, but again, it doesn't exactly matter, and that's the beauty of this design. The way that you make it work is you tap the line at a particular point. Generally, I would say about 1/4 to 1/6 of the way from the shorted end to the antenna end. So this distance here, D, must be found by experiment, and that is why this ladder line is so good, because it has bare wire. You can alligator clip your feed point right on there and move it until you get a standing wave ratio of 1:1 with your coaxial cable feed line. There's your coax. The shield of the coax, ideally, or the braid, should go to the non-antenna end or side of the transmission line. The center conductor of the coax should go to the antenna side of the line, and they should be at the same point on the line, both of these, and then you simply move that. You have an SWR meter here, and finally your radio here, your transceiver right there. You move this tap until your standing wave ratio is 1:1. Now, assuming 50 ohms of coaxial cable, you're going to have 0 ohms here, increasing. Always a non-reactive impedance appears when you tap this line, but it gets higher and higher and higher until it reaches about 2,000 ohms or whatever this happens to be at the antenna end. But somewhere along here, there is a point where this purely resistive impedance will exactly equal 50 ohms. That is, in fact, a J-pole, and because it is this particular length of line here can be just elevated a few feet above the ground, or even run along the side of a wooden building, or just as long as you don't lay it right on the ground or run it right on a metal surface. Just like any transmission line, it is a quarter wavelength section like this. So what you have here might be called a lazy J. Sounds like the name of a ranch, doesn't it? Well, I'd probably go for an antenna something like this at the Long Wave Ranch near Cody, Wyoming, if I ever move out there. But it's a pretty modest little digs on that land, and I like my house here in the urban crowd, the urban congestion of my hometown of Lead, South Dakota, in the Black Hills. QRN, QR Nancy, and all. It's not Nancy anymore, is it? It's November. QR November. Well, on 160 meters, the worst QRN you're going to get is not in November, but in the summer. The winter is the best time to operate on 160 meters. So I would assume, to begin with, it'd be about 122 feet for this length of line here. And what did I come up with? Pretty 252 feet or something, 258 feet, something like that for this line. Not a small antenna. And if you do fly a kite in a balloon antenna, you need to do several things for safety precautions. You need to contact the Federal Aviation Administration to be sure that you're legal. You need to tether it with a separate line so that it can't snap off and blow away. You need to make sure that it will not fall on anything where it can do any damage or create a hazard for anyone or any hardware. In particular, that it can't fall on a power line. So a lot of things you've got to do with an antenna like that. But at the Long Wave Ranch near Cody, Wyoming, that property is tailor-made for this kind of thing. Wind and all. Stan Gibilisco, proprietor and operator of radio amateur station W1GV, Whiskey 1 Good Vibrations, signing off for now. Until next time, 73 and so long.